Hey, the plants! They're dead!
These plants? It's the weather, the air, the water, the heat, and all of it and above. Welcome to Qatar, a land defined by its unforgiving heat, burning deserts, and absence of actual greenery.
It is a country where the land is dry, the air is humid. The rainfall so seldom, the market passes a holiday. The natural climate is just so ever deadly to our plants' lives.
But it's not just here. It's a problem in every humid center point of the world.
So, what do we do?
If you want to get this more, go to Gizmo.
In this harsh environment, we make growing nothing a challenge to the power of science and the capacity of one's ingenuity, innovating something and changing the game for such desert countries.
Qatar succeeded to adding greenery into places so vibrant you wouldn't believe that 40 degrees Celsius is the norm around.
But there's a catch. It's expensive. Qatar still relies on trading its natural gas and oil to buy soil fertile for its growth, as well as extensive artificial components in its system.
Qatar's natural environment is one of the world's most inhospitable to agriculture. From its scorching heat soaring beyond 50 degrees Celsius to salty soil, heavy humidity, and absence of freshwater sources, all the factors combine to create an ecosystem where plants simply cannot survive.
Humidity? You said humidity? That's everything we need.
If moisture in the air can efficiently be condensed using a low-energy cooling method,
Then it is possible to create a sustainable water collection system paired with calculated light frequencies to provide a constant water source for hydroponic farming.
Because atmospheric humidity is a widely available resource that can be harnessed without relying on traditional water supplies.
Amidst all this difficulty, we've developed a system that harnesses these hot and humid conditions into something more useful. We've made a way to grow plants efficiently, channeling these environmental elements into sustainable solutions.
So we built a basic hydroponic system. No soil, just water, nutrients, and plants. As well as LEDs that provide the specific spectrum for photosynthesis to occur.
Hold on. Let us split it into three major parts. The Peltier module, the hydroponic farm, and the wavelength-controlled LED.
Okay, let's begin. How do we get the water?
That's where dehumidifier comes in. Instead of relying on scarce fresh water or expensive imported water, we're pulling water out of thin air. Literally.
We were able to get the interior of a dehumidifier, including its heatsink and fan.
The fan collects the humidity of the air, then the metal plate at the bottom cools the air, producing water. When water is produced, it travels through the pipes, watering the plants.
This works because of relative humidity.
Relative humidity?
It is how full the air is with water vapor. If the air is already full, water can't evaporate. But if the air is dry, water evaporates easily.
And if it can't evaporate, you're bound to resort to condensation.
Using the Gizmo simulation,
We figure the relative humidity changes with moisture content in the air. So if the relative humidity is higher, there are more water molecules in the air sample as seen in the picture. So the dew point is at the temperature where the water vapor turns back into liquid. In hot, humid places like Qatar, the dew point is high. Just like a real dehumidifier in a bucket, it pulls in this humid air and passes it over cold coils that are colder than the dew point. In the Gizmo, the water bucket shows when condensation is happening.
Now you might be questioning, how are we going to keep the water from holding?
Basically, we will have these holes that serve as ventilation for the plants.
and you drain the water and the waste compost nutrient solution, and voila! That's how our system works in a nutshell.
On to the next part, the hydroponic farm. Using the Gizmo simulator for photosynthesis, we tested the possible conditions for the plant, taking factors such as light intensity, light wavelength, CO2 concentration, and temperature to see the influence on oxygen production, our basis for determining the optimal variables.
We put in the constants of two conditions, the respective temperature during the hot and cold seasons and the constant carbon dioxide levels. We varied the variables of light intensity and light wavelength in intervals of 15 in the respective situations. Then we troubleshooted to find an exact value when the threshold is reached.
For colder conditions, we tested 6 percentages of light intensity, finding out that above 65% produces optimal oxygen production, as well as 5 examples of light wavelengths leading to 450 nanometers. Thus are the optimal conditions.
For hotter conditions, we tested 5 percentages of light intensity, finding out that above 15% produces optimal oxygen production, as well as 5 examples of light wavelengths leading to, again, 450 nanometers. Thus, these were the optimal conditions we implemented.
We maintained the 450 nanometers as seen in the previous Gizmos. Using the Arduino Uno, a real-time clock module was set to have its self-sufficient clock to open its light at night and close at day.
We believe that this invention aligns with the SDGs 2, 11, 12, and 13.
And also the Qatar National Vision 2030
under the environmental pillar.
It only takes one action. It's our turn to greenify cities with every material we have to break through agriculture innovation and bring a change to further improve on our ideas.
Because the future isn't something we wait for.
It's something we build.